Okay, so thanks a lot for the invitations. So this is a joint course with George Boxer, and actually our goal is maybe a bit ambitious, but we'd like to report on some recent progress in the field of, I would say, p-adic geometry, and maybe provide an introduction to such results. Okay, and well, so some of the references, or at least so some of the people who have that we were inspired by this lecture are on the board. Okay, so let me and we'll try to write. Okay, I cannot do this, right? No. Okay. So and maybe we'll try to post notes also as the course advances. All right, so let me introduce the question and topics. Okay, so I start with a Shimura datum, Gx, but honestly, I think that whenever I give a proof, I will assume that Gx is GL2 over Q, and X is P1 of C minus P1 of R. So that's the Poincare space, okay, or the upper and lower half space. Okay, so I will also have a preferred prime number, okay, and then I fix some K, which is a compact open subgroup in the finite adels, which I also want to write in the form Kp, okay, the prime to P part and the P part of the compact. Okay, and so we can consider the modular curve. Okay, I will write it like this, SGXK, so that's the Shimura variety attached to Gx with level K, but I will abbreviate it by SK, of course. Okay, and so this is a curve over spec Q, and that's the moduli of elliptic curves plus level K structure. Okay, so for example, if K is the principal level N subgroup, then this is just the moduli space of elliptic curves with a basis of the N torsion. Okay, and then this has a toroidal compactification, but which in this case is nothing else than the canonical compactification of a smooth curve. Okay, and so this is SGX tor K, which I will also abbreviate to SK tor. Okay, so this still lives over spec Q, and this is the compactification. All right. Okay, so now there are two ways to think about, I think two main ways to think about modular form. Okay. Okay, so the first way, which is perhaps the most elementary way, like in Serre's book, Cours d'arithmétique, okay, you can think of modular forms as some coherent cohomology classes, okay? So that's the coherent perspective. Okay, and so one can consider the groups HI, SK tor, omega, maybe, okay, I will use, so K is an integer, okay, and maybe I will use some shift in the weight, so omega K plus 2, and maybe there can be optionally a cuspidal, so this is optional, okay? Okay, and so these are, and so what are these? So these are finite dimensional Q vector spaces with an action of the Eichler-Shimura. Okay. right? That's option. Okay, and okay, so really, I mean, so I'm doing a curve, right? So I have only h0 and h1. So usually people only consider h0, but you can also consider h1. But in this case, they are related by third duality. So that's maybe a side remark, is that here we have third duality, which actually identifies the dual of the space of the degree 0 cohomology with the H1 cohomology in weight. So I'm in weight k plus 2, I go to weight minus k, and then I have to add minus k. Okay, so in that case, it may not be so interesting to consider simultaneously all cohomology groups, but I mean all degrees of cohomology, but yeah. But for other Shimura varieties, this can be interesting. Anyway, okay. Okay, so that's the coherent perspective. And then, yeah, I should have said also that omega is kind of omega E, which is like the conormative of E over S theta. Okay. All right. Okay, and then there's the Betti perspective. So. Okay, so that's another way to think about them. There's the Betti et al. Perspective. Okay, so now K is, yeah, so now K is bigger than 0. Okay, and I can consider the, so I can consider the H1 Betti of the C points of my modular curves with value in some local system, which is maybe the sim K of the Tate module. Okay, all right. So that's a sorry, and I can do this even over Z. So sorry, so even the sim K of the homology, of the relative homology. Okay, and so that's Z, that's a finite type Z module. Plus an equaction. Okay, but one can also do this p-adically, and so one can consider the H1 et al. Of SK base change to Q bar, but now we have to choose some prime. So we can take the sim K of ZP square, so the sim K of the Tate module. Okay, and that's and now this is a finite type ZP module, and it has an Eichler cross GQ action. Okay, so one can do all this, okay, and these are two ways to think about modular forms in the sense that both cohomologies are computed by automorphic forms. And note that in the first coherent perspective, you see a little more modular forms because you see weight 1 modular forms, okay, which is not visible on the Betti side. Okay, and now, well, so both realizations are related by what's called Eichler-Shimura theory. So Eichler-Shimura theory relates both perspectives, okay? Okay, and so there's maybe historically, or what's maybe considered as easier, is to do this over C. So, and that really means that we consider the modular curve over C, so maybe the underlying analytic space, and we also have C in the coefficients. And so in that case, there's this kind of Hodge theory. With coefficient. Okay. Okay. So that's like Hodge theory with coefficients. Okay. And there's also a story over QP. Okay. Okay, and I should say that, so this is equivariant. Okay, and so again, now the space is base changed to QP, so the modular curve is really considered over QP, and QP is in the coefficients as well. And so this is Falting's Hodge-Tate decomposition. And so one has that H1 now et al. Of Sk over Qp bar with coefficients in sim k zp square. Sorry, there was a square missing here. Tensor Cp over Zp. This is kind of the same. Cp twisted -1 minus k, so there is a Tate twist, plus H1 Sk tau omega minus k tensor Cp. Okay, and so this is isomorphism is echo cross GQP equivariant. Okay, where, well, here the action of GQP is really on both. I mean, it extended by semilinearity from the et al. Cohomology. And here it's trivial on those two vector spaces, and it's only on Cp with the Tate twist and Cp. Okay, all right. So now okay, so now, well, now there's, okay, so not only do we want to do modular forms, but we often want to do p-adic modular forms, okay, or p-adic automorphic forms. But automorphic forms, by definition, this is I mean, this has some transcendental definition, okay? It's really a kind of Archimedean type definition, and p-adic automorphic form should be some kind of p-adic completion of the space of automorphic forms. But so to perform the p-adic completion, you need to choose some rational structure, okay? Okay, and here, well, we have two candidates for rational structure. Either we can use the coherent rational structure, or we can use the Betti or et al. Rational structure. And actually, each of these rational structures give rise to a theory of p-adic automorphic forms. Okay, so similarly, for p-adic automorphic forms, we have two perspectives. Okay, so the first perspective is the coherent perspective. Okay, and so that's really what's maybe the theory of higher over convergent modular form. Okay, so that was kind of introduced in the morning lecture by Alicia, at least the theory of over convergent modular forms, but there's really no reason to just do over convergent modular forms. You can also do a similar game with higher coherent cohomology. Okay, and that's what's now called higher Coleman theory. Okay, so let me just give a little bit of information on this. So for any k, yeah, okay. So again, so let me take k in Z. And so what we have kind of seen this morning is that, well, we have the space of classical cohomology. So maybe now I'm secretly over QP. So these are white K modular forms, and then one can actually restrict this to a space that's often denoted by m-dag k plus 2 of k, okay, and this is the space of over convergent modular forms. Okay, so these are, I mean, if you want, you perform some restriction from the entire modular curve to some neighborhood of the ordinary locus, or certain locus in the ordinary locus. I mean, certain components of the ordinary locus. Okay, all right, so we have this map. This is an injective map. And I actually typically will want to do the following. I also, well, it turns out to be kind of a bit useful for the formulation of the results is to really pass to the limit over the level at P, okay? So I can really pass to the limit over the level at P, or rather the co-limit, okay? And so I can take the co-limit. So maybe I should raise a little bit the blackboard. So okay, and then I can similarly here pass to the co-limit over the level at P, and then I have some space that I will now give another name. Okay, and that's I want to denote by H naught identity K plus 2. Okay, so I mean I think, well, this is the notation we use in the higher Coleman theory, and the identity refers to some element of the Weil group which parameterizes the Brouwer stratification on the flag variety. But this will come later. But yeah, let me just use this as a notation. Okay, so now this is what is this? This is this now has a BQP action, an action of the Ecker operators away from P, and this is an LB space, so inductive limit of Banach spaces of compact type. Okay, but this is this is definitely infinite dimensional. Okay, this is a rather big object. Yep. So sorry. Oh, sorry. Yeah. Okay. Yeah. Excuse me. Yeah. There is no. Yeah. It's a mistake of notation. Sorry. Thanks. Okay. All right. And there's a similar picture, but with the H1, but it's kind of reversed. So let me just like without being too precise. So I have some higher Coleman theory, which is H1 W naught. So W naught is another element of the Weil group of GL2. There are two elements. So same weight. Let me use minus K now. And then this will surject onto the co-limit of the H1 SKP KP tau omega minus. Okay? All right. Okay, so that's the current side, but I should maybe say one thing that's kind of interesting, and so that's maybe a remark, is that on I mean these cohomologies, so these higher Coleman theories, they actually make sense for K in CP. Okay, so you can now really allow your weight to be any element in CP and not just in Z. Okay, so that's, yeah. So there are many more sheaves, and there's really room to see families of modular forms. Okay, all right. So now let's come to the étal side of the picture. Okay. And so on the étal side, so your rational structure is really given by the étal cohomology or the Betti cohomology. And there are several theories that have different flavors. So I think the most general one is the one that's introduced by Emerton, and it's called completed cohomology. But there were other theories, for example, series of modular symbols, of over-convergent modular forms, etc. But it turns out that from completed cohomology, one can really recover this series. So let me just use completed cohomology. Okay, and it's really the most general, I think, completed cohomology. Okay, and so what's the definition? So H tilde I Kp is going to be, so an inverse limit of a colimit of the Hi et al. S Kp Kp q bar with coefficients in Z mod P to the NZ. Okay? Yep.
It makes sense for, so if this K is the P on the weight space.
Well, okay, it's true. So now I'm kind of, so now my parameter is actually the derivative of the usual weight. And the reason for this is that when I pass to the colimit over all time level, I'm kind of adding all Nebentypes at the same time. So I'm dealing with all forms of weight K and any Nebentypes, right? And therefore, it makes sense to use as a parameter not the actual weight, the p-adic weight, as we saw this morning, but rather its logarithm. Because any two weights with the same logarithm will differ by a finite order character. Yeah. Okay, but that's, you're right, yeah. Okay, and then I invert P. Okay, so that's rational complete cohomology, and so this is now a Banach space. With a GQ cross G of QP cross away from P action. Away from P action. Okay. All right. Okay. And now, well, now so, yep. Here, do we take a colimit? Yeah. Yeah, we take the colimit over all time level. No, it's really a colimit, yeah. Thanks. Oh, okay. So let's see. Yeah. Okay. Okay, all right. So now, yep. So now it makes sense to ask the same question as before. I mean, is there a way to compare both series of automorphic forms? Okay. Right. Okay. And so we have this p-adic Eichler-Shimura theory, which was actually initiated by Andreatta, Jovita, and Stevens. Jovita and Stevens. But really, there was, I think, a really change of perspective with the work of Pan, and I'm going to state the result for you for the modular curve. So that's the following theorem of Pan. All right. So first of all, so let me just state the theorem for integers, but there's actually a theorem that goes beyond integers. So for any k in Z, there is an exact, there exists a sequence, so we have a complex. So the complex is like this, so you have 0, H1, W, 0, minus k, now you go into some space which is a bit complicated, but I will say in a second what this is. So I take the B cohomology of the weight K acting on the locally analytic vectors of the degree 1 completed cohomology. Okay? And then this goes to H naught id K plus 2. Okay, I mean, yeah, I think that, well, these are maybe now everything is defined over CP anyway, but let me just add the Tate twist, -1 minus K. Okay, so we have such a sequence. Okay, so we have such a complex, which is, so here, maybe I can use colors. So LA refers to locally analytic vectors. Okay, for the GL2 QP action. Okay, and maybe B is the Lie algebra of the Borel. Okay. Okay, and so when I take locally analytic vectors, I have an action of the Lie algebra, and so it makes sense to speak of this home space. And K is viewed as, in an obvious way, as a character of the Borel. Okay, so now this, and so and these are the two higher Coleman theories. Okay, so now this, the sequence is exact. Is exact if K is strictly less than 0. So that's basically in the range where actually there is no classical automorphic sheaf. There's no sim K of the standard representation, right? And now if K, now on the contrary, if K is bigger than 0, then actually so this map is still surjective, so we actually get, so we actually have okay, and now there is a space N, and actually N is very similar to this higher Coleman theory, but like it has the same Jordan-Holder factor, but they are in the opposite order. Yep. Like this mean? You mean? So I only said it with words. So I take the locally analytic vectors. K is an integer, and so I can think of K as a character of the Borel, right? Because I project the Borel to the carton. Okay, I'm cheating a bit between GL2 and SL2, but this is usual. Yeah. Let me write it. So I have B, which surjects onto H. Okay, and H is really, I mean, this is GA if you want. This is the. Okay, yeah, is it? No, it's confusing to write GM, maybe, I don't know. Okay. Anyway, H is, okay, or maybe, well, that's the Lie algebra of the torus, and then I can use the map K, yeah, I mean, yeah, so I guess it's, okay, there are many possible identifications, but yeah. So that's, I view K as a character of the Lie algebra of the torus, which is GA. Okay, I think, yeah, sorry. Yeah. Yeah? What does it mean? Well, so if you want, H is as one element, is gen.
Is the isotypic part?
This thing, yeah, exactly. Then it's the isotypic part. It's the K. Yeah, it's the K isotypic part. Yeah. Okay. And so now, yeah, and so if K is, then N goes the other, like, so this N is very similar to this higher Coleman theory, but it's an extension the other way around. So actually it has, okay, it has actually as a quotient the space of, so this higher Coleman theory in weight minus k, and it has as a sub the classical H1 cohomology. Okay, well, anyway, that's, yeah, I think you can read the details in Way's paper, but okay. But so, anyway, I think, yeah, so what's interesting is that such a decomposition still exists, yeah, and actually you can in fact describe its shape, even though the shape of the decomposition is not uniform on the weight, okay? Like, so over C over QP, we had some really uniform decomposition on the weight, like there's an easy recipe to pass from the automorphic weight to the coherent weights. Here, the recipe really depends on whether K is positive or negative, right? Okay, and that's really a feature of the theory, and it's quite interesting to understand what happens, and it's extremely mysterious. Okay, so okay, and so I would say that one of the goals of the lectures is really to generalize and explain. I mean, so explain the explain this decomposition for modular curves, and maybe also to state theorems that hold for general Shimura varieties. Okay. Yep.
This is W0 and E.
Yeah. Okay. So.
The definition is the same.
No. Okay. I didn't yet give the definition. So this morning you saw the definition of what I'm calling now H0id, okay, which is over convergent modular forms. Okay. But I claim that there is also a definition for the H1 cohomology. And basically, I mean, the idea in this case is that instead you consider the H1 with compact support of basically, I mean, of something, well, not quite the ordinary, I mean, yeah, of the ordinary locus in forced approximation, or sorry, of some neighborhood of the ordinary locus.
There is also an H1
There is also, yes, no, but okay, but I mean, you can define it, but it will turn out to be 0 because these neighborhoods of the ordinary locus, they are affine, okay, and so on an affine space you don't have. Okay, yeah. Okay. All right. Okay. So, yeah, maybe just before moving on, I can maybe just make one more remark. Is that also this decomposition? This is really GQP equivariant. Okay. And yeah. And so again, you have GQP action. Yeah. Okay.
The last question.
Yep.
The -1 minus k is a twist.
Yes, and this is a Tate twist. Okay, and well, now that you ask this, I cannot resist to say that actually, when if k is different from -1, then the Sen operator is semi-simple. Okay, because the Hodge-Tate weights are different. But actually, when k is -1, the Sen operator is not semi-simple. And this is really interesting also. Because now the two Hodge-Tate weights are 0. Okay, and one can study the semi-simple part of the Sen operator. But that would be the topic of another course. Okay, all right. So, okay, so that's maybe the rough goal of the lecture is to explain all these theorems and also I think explain all the geometry that is behind these theorems, and that's now maybe called geometric Sen theory. Okay. But so today, as a little warm up for this geometric Sen theory, one introduces a bunch of incarnations of the Shimura variety, the different p-adic incarnations. I want to start by doing this algebraically and to speak a little bit about, so not only the algebraic Shimura variety, but also it's the Rham stack. Okay, and to explain a little bit of this geometry, because this can really serve as an inspiration for generalizations that will be made in the other courses. But honestly, it's not absolutely necessary for all we have to do. So if now you don't understand anything, it's okay. All right. So okay, so now I want to speak about the Rham. So maybe that's really like the main topic. This is the Rham period map. Okay, so the Shimura variety is usually a bit complicated, but we like to have period maps which really help us and tell us what to do. Okay, so the first classical thing one can do is really work over C. Okay, and so we have this, so now I have this S, G, X, K of C, okay? So that's the C point of the Shimura variety. And this I can classically write as a finite union of quotients of the locally symmetric space by groups, gamma I, which are congruent subgroups of G of Q. Okay? All right. So now what does one classically do? You can consider, well, this kind of universal cover. So that's X, okay? And this now X embeds into its compact dual, which is the de Rham flag variety. Okay? So this map, okay, and I will say what's going on in the case of modular curves in a sec. So this map is really an étal map for the group gamma I, at least if I make a number of small assumptions that I'm going to make, and yeah, okay. And this map is an open immersion, and this is called the Borel embedding. Okay. Well, okay, it's an immersion on each. Okay, yeah, it's an immersion, it's an open immersion on each component. Yeah, okay, so that's a slight abuse of language. Thanks. Okay. All right. So now, okay. So yeah, so let me just, give just the example of what's going on. So so in the case of modular curves, then, well, so I have this X over gamma I, then over it I have X. So what's X? X is really it's really the moduli space of elliptic curves plus a trivialization of the homology. Mm-hmm. Okay, or if you want, this is just a moduli space of Hodge structures on Z2. Okay, and then we have this map to P1 of C, okay, which is, in that case, FL de Rham of C. Okay, and that's just that you take your Hodge structure and you just look at the corresponding Hodge filtration. Okay. All right, so this is what we have. Okay, and so in general, FL de Rham is G over P mu standard, and so that's, yeah, and so P mu standard is a parabolic that's attached to the Shimura datum. But okay, if you've never seen this, it's fine. Let's think about the modular curve. Okay, so now this picture is quite good, right? Because really it tells us that the C points of the Shimura variety are very closely related to that simple space. Okay, the de Rham flag variety. Namely, you have this étal map and then you have this open. So in particular, we can use this diagram to pull back and descend equivariant objects, maybe G equivariant objects on the Rham flag variety. Okay. All right. So let me give examples of this in action. Okay. So the thing that we classically do is that if we have a representation of G, okay, on a Q vector space, so this has maybe finite dimensional representations of G on Q vector spaces. Then you get a Betti local system on Sk of C, okay, just by mapping V to the space of sections of V cross X divided gamma I to X over gamma I. Okay, so that's like a classical construction, and this was basically the definition of my sim k zp square underline, okay, or sim k z square underline, or it would be q square, yeah, but maybe. Okay, so another key example is so these are called automorphic local systems. Okay, and then another key example are the so-called automorphic vector bundles. So now you start from, okay, it's a bit more complicated, but you start from coherent sheaves on the quotient stack G modulo FL de Rham. Okay, so I will say in a second what this is. And then you can arrive to coherent sheaves on Sk of C. Okay, and so these are the so-called automorphic vector bundle. Okay. Okay. So what's the procedure is that basically if you have a sheaf here F, you can take the restriction of this sheaf to X, okay, the period domain, and then you can take the projection of your sheaf down to X mod gamma I, so let me call this pi, and now this projection will inherit a gamma I action, and so you can take the gamma I invariance. Okay, well, that's a construction you can do, and then it turns out, but I will maybe say a little bit more in a second, is that actually these, okay, so maybe I'll write this up here. Okay. Okay. What? Okay, but yeah, I think it's fine. Okay, and here, and maybe here, G modulo FL de Rham, these are by definition G equivariant sheaves on FL de Rham, and I mean, if you play a little bit with, okay, I don't know, if you're familiar with stacks, then this is G mod P mu standard And so this is just the classifying stack of p-mu standard. And so these are the same thing as representations of p-mu standard. Okay? All right, so the idea is that if you have a G equivariant sheaf on this de Rham flag variety, since G acts transitively on the de Rham flag variety, G equivariant sheaves are the same thing as representation of the stabilizer of a point. And the stabilizer of a point is the parabolic. Okay? So that's fairly standard, right? And this, well, and therefore you get a recipe to attach to any representations of p-mu standard some automorphic vector bundle. Okay, all right. So now, yep. Yeah, exactly. Okay, so let me give an, yeah, okay, very good. So let me maybe give some example of this. Okay, I was planning to do it later, but I think it's actually better to do it now. So let me assume that my group G is GL2. Okay, but again, I will do this. Now I do this abuse of notation. I will really think of SL2. Okay, I think this is common. Okay, so now using this dictionary, there are really so therefore in that case p-mu standard is really just the Borel B. Okay, and now, well, I'm telling you, you have a functor from representations of the Borel to, well, even coherent sheaves. So I'm considering finite dimensional representation to coherent sheaves or even vector bundle on this Shimura variety. Okay, and so inside the representations of the Borel, you have the representation of the torus. Okay, and so the representation of the torus, so the torus is GM. So its simple representation are just rising to the k's power where k is an integer. And so inside here you have k in Z, which is going to go to omega k. Okay, so that's okay. That's how it works. But you can also really consider a representation of the Borel itself that are not induced from the torus. Okay? And so in particular, if you took the standard representation, so maybe let me write Q square, okay, which is acted on by the Borel, then you get the so-called H1 de Rham, so the relative de Rham cohomology of the universal elliptic curve over Sk of C. Okay, and well. And it turns out that, well, now any representation of the Borel is a tensor product of a representation induced from the torus and a case symmetric power of one of these guys. And so all the sheaves you get that way, they are the sheaves of so-called nearly holomorphic modular forms. Okay, that you may have seen in some talks. Okay, and so you get them all that way. Yeah. But yeah, what I want to say is that when you first study, I don't know, modular forms, okay, I think the definition is a bit bizarre, and then you wonder, okay, why are the weights of modular forms integers? Okay, and this kind of picture is really telling you how to produce in complete generality coefficients for modular forms over more general Shimura varieties. They should really arise from representations of a certain parabolic which is attached to the co-character mu of the Shimura datum. Okay, so that kind of gives some framework where you can understand things. Okay, so now, okay, so that was good, but that's really just something you can do over the complex, and this is not going to generalize because this construction really all relied on trivializing the homology with coefficients in Z of the universal object. But this is not something we can do over algebraically. Okay, so now there is a replacement for that picture algebraically that I'm going to give now. Okay, so now that's maybe I want to state a few algebraic theorems. Okay, so of course the first theorem that was already implicit is that I mean, that was implicit in the case of modular curve, is that I always have a canonical model for the Shimura variety. So this is the, so there exists a canonical model over a number field egx, okay? But if we do modular curve, we don't have to really worry about this because we already define this canonical model as some moduli space. Okay, but let me say that this is something quite general. Okay, the second theorem is, which is quite good to speak about coherent cohomology, is to have compactifications, because otherwise when you take the cohomology of this non-proper guy, you might get something enormous. And so the second theorem, which is theorem of Faltings and Chai, is that there exist compactifications. Okay, and I think we will care mostly in these lectures about toroidal compactifications. Okay. Okay, but again, in the case of modular curve, it's not too complicated. Okay, and there exist smooth compactifications, and the complement, I only say this in word, but the complement is a strict normal crossing divisors. At least, well, this compactification depends on some auxiliary choice, but yeah, so maybe I write it. So there exist smooth compactifications depending on combinatorial choice. Combinatorial choices. And the complement SGX to K minus SGX is a strict normal crossing divisor. Okay, so that's also important. All right, and so now let me state the theorem that is a good replacement for. Oh. Yeah, exactly. So it means that the irreducible components are smooth. Exactly. Yeah, exactly. So you cannot have self-intersection. Yeah. Mm-hmm. Ah non, ça j'ai pas le droit, c'est ça. Okay. All right. So, okay. So now, what's the replacement? Okay. So the replacement is the following theorem. So there is a Cartesian diagram. Okay, so here I put the Rham flag variety, which by the way really lives over the reflex field. Okay, divided by G. Okay, so that's a stack. Yeah. Then below I put the Rham stack of that Rham flag variety divided by G. Here I have the Rham stack of my Shimura variety, and above I have the Shimura variety. Okay, so that's a Cartesian diagram. I will explain. So the goal for the remaining time is to explain the terms in this diagram and to explain how the proof of this Cartesian diagram goes and how you use it. Okay, what is this good for? Okay, and really don't be afraid. I mean, it's just a way to, I would say, efficiently gather things that you already know. Okay, but once you do this, then yeah, I think it can be quite powerful still. All right. So just as a remark, I should say that there is a version. There is a version with the toroidal compactification, but I think it's fine to not talk about it. Okay. All right. So. Yeah, absolutely. Yeah. That's the key point. Yeah, that's the key point. It's not a G, the Rham. It's a G. Okay. All right. So now I have to quickly tell you what is the Rham stack. That's the first thing I have to tell you. Okay. So. Okay. So definition of Simpson. So X scheme. So one define X the Rham. So the R point of X the Rham, where R is a ring, this is X of R red. Okay. So R red. This is the associated reduced ring. So so that's called the Rham stack. But the proposition is that X the Rham is actually an étal sheaf. Okay. Sorry, which? Yep. Yeah. Oh, it should have been there also. Thanks. Yeah. Sorry. Thanks. Okay. So X the Rham is an étal sheaf. You can check this with your hands. I mean, it's clear that it's a sheaf because this is its values are sets. Okay. And then the fact that it's an étal sheaf is an easy property I mean, like if you have an, okay, maybe let me sketch a proof actually. Okay, so let's take R2S be an étal cover of rings, okay, and then I want to check that X the Rham R goes to X the Rham S goes to X the Rham S tensor R S. I want to check exactness here, but this is by definition X of R red. This is X of S red, and this is X of S tensor R S red. Okay, and so so the key property I want to use is that actually S red is S tensor R red. Okay, so that is if you're étal over something reduced, then you are reduced. So it's something you may know for fields, for example. If you're étal over a field, then you're a product of separable field extension. Okay, there are no nilpotents. Okay, and therefore this diagram is also I mean S red to R red is also a cover, and this is S red tensor R red S red. Yeah, and so this follows from the sheaf property for X. Okay, all right. So now when you have a stack or a sheaf even, you like to have presentations in terms of maybe schemes or okay, and so for the Rham stack this is actually possible, at least in some cases. So in the smooth case. Okay. Huh? Yeah, exactly. I should say that this is not the only definition of the Rham stack in positive characteristic. There is another definition of Batt and Lurie that is better. But okay, so maybe I mean that's really a proposition. So assume that X over Q is smooth. Then X to X the Rham is, well, actually, yeah, okay. that works over any field. But anyway, it's just that the category of sheaves is not the good category. But that would also work in epimorphism. And moreover, X cross X de Rham X. This is the completion of X cross X along the diagonal. That I want to call maybe delta at. Okay, and so this is, which I really think as the co-limit as n goes to infinity of the vanishing locus of the ideal of delta to the nth power. Okay, and so maybe this I want to call delta index n. Okay, and I delta, this is okay. I think it's clear. All right. So, okay. So in other words, we have a reasonable presentation in the smooth case of the de Rham stack as the quotient of X by an equivalence relation, which is given by you complete along the diagonal in X cross X. Okay, so the proof. So first, what is this map? Okay, I wrote like that there is a map as this was obvious. Well, I mean, if you unravel the definition, this is indeed clear. So the map is the map. So if you have, so you indeed have a map from X of R to X de Rham of R, because this is just X de Rham of R. This is just X of R red. Okay, and so this map is really that you have an R point of X, but inside spec R you have spec R red, and so you can compose with this map, and you get now a map of an R red point of X. Okay, but actually one can actually lift, and this is like we use the formal smoothness. Okay, so actually since X is over Q is smooth, so it's finite type, so I can really assume that R is also a finite type, and therefore R to R red, the kernel is a nilpotent ideal of a bounded degree, and so I can successively lift, and then I can find a lift, and okay, I'm good. I mean, there's a little finiteness argument going on, I think. All right. So that proves that actually the map is literally surjective. Okay, and now we need to understand. So we need to understand the equivalence relation. Oh, no, this I cannot do. So we need to understand the equivalence relation, and so what's okay, and so I claim that X. Okay, let me just say it in words. So what's X cross X de Rham X? It means that I have 2 points, 2 R points of X, and but when I look at the restriction to the underlying reduced ring, then these 2 points are the same. Okay. And so now it means that actually the difference between these 2 points is in some neighborhood of the diagonal. Okay, you just write it, replace X by an algebra, and you will see it's clear. Okay, all right. So that gives us a presentation. Now I want to say some remark, maybe some intuitive way to think about this de Rham stack. So if you see what's this V of I delta square. Okay, so I take the second neighborhood of the diagonal in X cross X. Then this is really X cross its tangent space. Okay, and so it means that so now because of this one can really think of X de Rham, and one often writes X de Rham as being X divided by the tangent space. But what one really means by this, okay, is that actually so delta at is a groupoid, okay, and any points which differ by an ideal which has degree of nilpotence n can be successively approximated by points which differ by an ideal of nilpotence 2. And so that means that actually this second neighborhood of the diagonal, it actually under the equivalence, under the groupoid law, it actually generates the entire delta hat. And so by just making this identification, but I don't know, passing to the, I mean, saturating, I mean, the equivalence relation, we really get some feeling for this, right? So okay, sorry, that was a really bad explanation, but I hope you could follow me. But yeah, okay, and now, okay, so that's okay, so that's one thing. Okay, now why is the Rham stack good for? Okay, well, the Rham stack geometrizes the module. So again, X over Q. Now it's key that you over Q. Then actually Q co over this Rham stack. These are quasi-coherent the X modules over X. Okay, so well, I mean the proof is basically amounts to write, I mean to revisit Grothendieck's perspective on the infinitesimal sites and modules with stratification and the modules. But so we have this. Okay, so we have this presentation of the stack, which is given by this, and so really by definition of how you attach a theory of quasi-coherent sheaf to a stack, then you deduce that quasi-coherent sheaves on X the Rham are just given by the limit of this diagram. So you have quasi-coherent sheaves on X, and then you have quasi-coherent sheaves on X cross X the Rham X, and okay, then you need to continue. Okay, but so now if you so now let's try to understand what's an object on the as a quasi-coherent sheaf on the Durham stack. Then first of all, I have to give myself an object here. So this is some F, which is a quasi-coherent sheaf on X. Okay, and then I have to give an identification between the two pullbacks. And so I really need an identification between the two pullbacks, P1 upper star, P2 upper star F. But okay, and now, well, it turns out that if you now restrict this identification to the first, so the second neighborhood of the diagonal, then that map is really given by F goes to F plus nabla of F, where nabla is a connection. Okay, and well, and then there is some co-cycle condition that ensures that the connection is integrable. And okay, and now, and by this I've just really roughly explained how to go from a sheaf there to a dx module. Okay, and then one can go backwards also by similar computations. Okay, good. So now, okay, and maybe one last thing I just want to say, but maybe I don't have really much time to say more, is that actually if you take two sheaves on X, okay, then there is a notion of linear map from F to G, so that's just a morphism in quasi-coherent sheaves over X, but there is also a notion of differential operator. And so differential operator are maps which are not quite OX linear, but not so far from being OX linear. And actually, from that perspective, it's very, there is a very clean, I mean, it basically follows from the definition. What's a differential operator from F to G? Well, this is actually a map, but over the Durham stack between the push forwards of F and the push forwards of G to the Durham stack, where pi now is the map from X to X Durham. Okay, good. Okay, so now I start to run out of time, but okay, I think, so these are things I wanted to say about the Durham stack. So now let me come back to this diagram, and we've kind of defined what's the Durham stack, and so now we can try to prove that this diagram exists and is Cartesian. So now back to okay, so now the proof, so I want to construct and prove that this is Cartesian. So the proof is going to use, so of course I'm also doing the modular curve. And so the key ingredient, well, is everything we know, and we just put together, but really what we know in the case of modular curves, well, you have your universal elliptic curve over the Shimura variety, okay? And so you look at the Rham cohomology. So it's relative the Rham cohomology. Okay? So that's a rank 2 vector bundle, and it has a lot of structure. So what kind of structure does it have? It has a filtration. Okay, that's the Hodge filtration. It has a connection. Okay, I honestly, I don't remember. I don't, okay, but, well, now these are impossible to move, therefore. Okay, flip. Okay, so, okay, and then, well, it's okay. And so you have a connection. And then you have a Kudla-Spencer map, which is an isomorphism from omega. So this connection satisfies Griffith's transversality, and therefore you get a linear map from omega e to omega e minus 1 tensor omega 1 sk. Okay, and that map is an isomorphism. So this is called Kudla-Spencer. Okay, so actually this diagram being Cartesian will be equivalent to all these ingredients. Okay, but now let me explain roughly what to do. Okay, is five minutes is okay? Yeah. Okay. 10? Oh, amazing. Okay. All right. So. Okay, so now, if I have 10 minutes, I may be right that this is Kudla-Spencer. Okay, right? Okay, but let me say that all these ingredients are surely familiar to you. Okay. All right. So now the first thing is that we want to construct this map. So SK to G modulo FL de Rham. Okay. So by definition, what does this map amount to? It amounts to a G torsor, okay, that I'm going to call G de Rham, and a G equivariant map from G de Rham to the flag variety. Okay, that's the point of the. I mean, just describing what's the point of the quotient stack. Huh? Sorry. Some arrow is wrong, right? Yeah, absolutely. Okay, all right. So now so we need this G torsor. So of course the G torsor is the torsor of trivializations of H1 de Rham of E. Okay. Okay. So that's a G torsor. Okay, and then this map is given, therefore this map, the map G de Rham to FL de Rham, is given by the Hodge filtration. Okay, right. So that's one thing. Okay, so the second thing is that now I can use Kudla-Spencer, and so Kudla-Spencer is telling me that actually, so let me denote by Q the map that goes from G de Rham to the FL de Rham, and by P the map that goes from G de Rham to SK. So Kodera-Spencer is telling me that P upper star of the tangent sheaf of the Shimura variety gets identified with Q upper star of the tangent sheaf of the de Rham flag variety, okay? Because the tangent sheaf of the de Rham flag variety is really O of 2, okay? And then O of 2 gets identified with omega 2, okay? And then this isomorphism, the Kodera-Spencer isomorphism, really then identifies omega 2 with omega 1, sorry, omega minus 2 with omega 1. So I have this, okay. Now, another thing is that the connection, so nabla extends to, so nabla is a connection on the sheaf H1 de Rham, but it actually then extends to a connection on the structural sheaf of G de Rham, which can be built from the vector bundle H1 de Rham by using tensor operations. Okay, that's something you can do with your hands. And so nabla extends to O G de Rham to O G de Rham tensor omega 1 SK. Okay, and so now what does this mean? This means that I get, in other words, I get kind of an action of the tangent sheaf of the Shimura variety, which kind of now identifies with the tangent sheaf of the flag variety on G de Rham. Okay? And so now I can use this action to actually, now actually I can take this diagram, okay? I can take this diagram, but now on this diagram, I've just explained to you that I have an action, compatible action of the tangent sheaf of the Shimura variety here and of the flag variety. And so I can mod out by this action to get the de Rham stacks. And so modding out, I get, and so I now get SK de Rham goes to FL de Rham mod G. Okay, and so that's because well, if you want, I have some FL de Rham, and here I have G de Rham modulo TSK. Okay, all right. So that's so now I've just constructed the diagram. Okay, like I have constructed the top map, but I also have constructed the bottom map, and it's okay. And it's from there it's not so hard to check that it's that it's commutative and Cartesian, but I will really omit the details. Okay, sorry, I'm kind of running a bit out of time. Let me now just finally say how to use this diagram, and I stop here. Is that okay? Yeah, 25 is okay. Okay, so all right, so now yeah, how to use this? Mm-hmm. Okay, so application. Okay, so the first application is that, well, if I only use the top map of the diagram, I get a pullback map from quasi-coherent sheaves on G modulo FL de Rham to sheaves on the Shimura variety, but now it's really the algebraic Shimura variety, not the Shimura variety over the complexes. And this is still Rham P mu standard, okay? So if you want, this gives models for the vector bundles, okay? So yeah, and this functor is doing exactly the same thing. I mean, I wrote some recipe for what the functor was doing in the case of modular curves, and well, this recipe obviously works at the algebraic level. Okay, so that's one thing we have, but there is another thing, and so it's the following proposition. So that's which is about differential operators. And so the proposition is the following. If I now take V and W, which are finite dimensional representations of P mu standard, then I have a map from the Helm space. Okay, it's a bit complicated. I take some Vermas, some parabolic Vermas, so as UG module from UG tensor UP W dual to UG tensor UP V dual to differential operators between V to W, okay? And maybe, okay, and so this functor is mapping V to some, maybe math V. Okay, all right, so, okay, so I claim, I don't have time to explain, but I claim that this proposition becomes extremely formal once you have written up this diagram. And to just give you just an illustration of this formula, let me just give one example. So let's do this for, again, GL2, which is SL2 for us. Then you know that you have a map from, then there is called BGG map from UG tensor UB minus K minus 2 to UG tensor UB K, okay? I hope, so these are the Vermas of weight minus K minus 2 to the Verma of weight K, that's for K, positive, non-negative integer. And so now if I apply this recipe, what differential operator do I get? I get the theta map that goes from omega minus K to omega K plus 2, okay? And so again, this theta map is not so hard to construct, but for more general Shimura varieties, it's good to have a general, robust understanding of how differential operators can be constructed, and this diagram is really giving, I think, very, very good answer. Okay, so I will stop here. Thanks.